Alors, bonjour tout le monde. Nous sommes très ravis d'accueillir l'astrophysicien Youssef Moulane. Alors, Youssef Moulane, c'est un astrophysicien qui a un très bon parcours dans le monde de l'astrophysique et de l'univers. Donc, il a commencé son domaine de recherche dans l'université de Liège, à Belgium. Donc, il a travaillé sur la photométrique, observation et monitoring. Puis après, il a commencé ses études sur l'observation, data reproduction and analysis of comets dans l'observatoire européen, dans European Southern Observatory en Chili, aux États-Unis. Puis après, il a fait un postdoc sur comet properties, composition and evolution, major research area, including planetary science in Oberon University dans les États-Unis. Puis après, maintenant, il est installé à l'Institut of Applied Science, Applied Physics de l'Université Polytechnique de le roi Mohammed VI au Maroc. Et voilà, donc aujourd'hui, Youssef Moulane va nous parler sur un brief journey dans l'univers, dont on va vraiment décrire le parcours de notre système à partir de notre système Soleil, puis après au-delà. Puis après, on va nous parler aussi sur l'activité de recherche dans le domaine astrophysique. Puis après, à la fin de la conférence, on va avoir la chance d'interagir avec lui, de poser vos questions si vous en avez. Et après, voilà, de aussi donner son avis sur la recherche en astrophysique et les obstacles qu'on a aujourd'hui dans ce domaine-là. Donc, sans tarder plus, donc je donne la parole à Youssef Moulane qui va nous donner cette présentation en anglais. Donc, et je remercie beaucoup pour accepter l'invitation et d'être présent aujourd'hui.
Merci Abdullah et merci collègues pour l'invitation pour donner cette conférence. Donc, je vais switcher en anglais, c'est comme ça, on fait toute la conférence en anglais, mais c'est pour les questions, si vous avez des questions à la fin en français, je peux répondre en français aussi, mais dans mes conférences, la plupart, je préfère de parler en anglais parce que ça me facilite les choses pour les mots techniques et ainsi de suite. So, my name is Youssef Moulane. I'm a research scientist at the University Mohammed VI Polytechnique here in Morocco. So I joined like last year. So as Abdullah described my journey, so I went to Europe and I was up before to go to Belgium. I was in Le Havre University, my first PhD year in Le Havre University. Then I did Belgium. Then I went to Chile for 2 years for working with ESO, European Southern Observatory. And then I went to the United States to work at Auburn University as a postdoc. So that's my journey quickly, but I will not include that in my presentation. So let's have as Abdullah told me, so you are studying all the physics and also the high energy physics. So we will also have some brief or a journey to the cosmos. And I will talk about that by starting raising this main questions, what we call the cosmic consciousness questions that we have as a human that we are asking, and we're still asking to understand everything around, many things around us. So the first question, are we alone in the universe? And I think you might have also asked this question. So, this is our planet. It's among 8 planets surrounding the star, which is our sun. And the sun is one of billions of the stars in our galaxy, and so on. So we know that there is other planets surrounding other stars, like we call them exoplanets, other planet. We have now found around like more than 5,000 exoplanets in our stars in our galaxy. So if you do like kind of small exercise of statistics, so you multiply that number of the planet of the numbers of stars that we know in our galaxy, which is one of billions of galaxies in the universe. That will give us trillions of planets that might exist. So the life exists only in one planet among of trillions of planets, similar planets on the universe. This is a probability or a statistic question that you might ask. So, and then we have raised this question, so are we alone in the universe? So we will be talking briefly in this conference about some efforts that we are doing, that scientists are doing for searching for the extraterrestrial life, including the microbial for life, for example, on Mars or in some places around in our solar system, and then outside of solar system, and around other planets and around other stars that are located in what we call the habitable zone. And also we are developing some techniques and some ways in some observatory to look for detection of signals of other advanced civilization if they exist. For now, there is no scientific evidence that they exist, this civilization, but they might exist. We should also develop in our technology and our observatories to look for this extraterrestrial intelligence by looking for the signals that might be coming from the other civilization. But this is also bring you to a little bit of science fiction. This is something that it might be exist too. The second question that we still did not understand: how did the universe originate and evolve? We are a part of the universe, and we don't know what's the limit of this universe, where this universe starts from. Talking about the Big Bang theory, formation of the galaxy, for the stars, for the planets, how the life emerged in the Earth, and including other planets and everything. So we still did not have a really complete picture how our universe works actually, or even how our planet was formed or our solar system was formed. So we're trying to study that and answer these questions, which is, I think, human nature. So we're wondering around ourselves and what is where everything is coming from and how the origin of things. So we are doing very good progress in that. So we will talk about that in the conference. And where we are, actually, this is like, it may be like a basic question, but nobody can answer you today where we are. Okay, so if you can consider, okay, we are in a planet, Earth, which is among 8 other planets around the star. Star is among of billions of stars in Milky Way galaxy, and the galaxy it's among clusters of galaxies in the universe. And where the age of this thing? So where we are, we don't know. It's people talking about that the universe is maybe just one of among other universe, what we call the multi-universe, that there might exist other universe in this multi-universe world. So we don't know really where we are in this big things, if you think big, of course. So that's what we call the cosmology, and we're trying to understand the evolution and of our universe and where it's coming from and so on. So all these questions guide our scientific research and also our philosophical reflection, and inspire the humanity to drive and to explore the unknown. And that's what we have been doing so far. So if we want to brief everything in this graph, so this is going to be the story of our universe. So most accepted theory for now is what we call the Big Bang. And nobody going to tell you what's happened before that Big Bang. And that Big Bang theory, actually, it's coming from the Hubble when he came with this idea that he found that the galaxy, they are getting away from each other. So a galaxy, it's a very mass of stars surrounding one center, which is a black hole. So he found that out that the galaxy, they are getting farther away. And this is where the expansion universe coming from. And if you think and revert in time, get back in time, you might to get to one point. So, and that point should be the Big Bang. And this is the explanation of the Big Bang theory. So now we have an estimation that the Big Bang, it's happened 14 billion years ago, based on what we have studied. And we still did not understand the few fraction of time of the universe when the inflation happens. So we believe that something has happened to inflation to make the universe as it is today. We still did not have much information about the dark age when before the first star was formed. And we still have many other mysterious things like the dark energy and dark matter. You know, that's all that we see today in the universe, all the galaxy and every star, the planets, everything we talk about today, it just represents 5% from the known matter that we know, which is called the visible matter, or the matter, ordinary matter that we know, which is the molecules, atoms, and everything we see. 95% it's made of dark energy and dark matter. This is our other matter. We don't know what they are yet, but we can see their effect on our evolution of the solar of the universe. If we want to describe how the universe it works today, we should to include this 95% made of dark energy and dark matter. And this dark energy, we call it dark because we don't know what it is. And there's a lot of effort in kind of theoretical and also experimental trying to identify what this energy is, which is mysteriously driving the evolution of the universe. For example, we cannot explain the evolution of the galaxies without including this dark energy. So let's take an example. So in our solar system, the planet that closest to the star, they are rotating or orbiting faster than planet, for example, in farther away from from the sun. And this is very basic physics law that we use, the Kepler motion of the planet. And this is for one that will, the one far away will be much, the gravity on the sun, it will be less than of this one, the closer, and then they will be taking much time to orbit around the star. And this is not the same thing happening, for example, in the galaxy. We found in some galaxies that the stars are far away from the center, which is mainly gonna be black hole because it's a very massive object. So the stars that far away from the center of the galaxy, they are rotating much faster than the stars are closer to the black hole. And that's made the scientists crazy. There is something gravitationally affecting this movement of the stars, which we name it dark matter. And also the dark energy is what is making this universe accelerating. So in this rate, which we did not understand yet. So what we could do today is just to study how this object is getting far away from each other, measuring that Hubble constant, which is now even still a debate. We don't have a precise measurement how the universe, the rate of the expansion of the universe, the value now is between 65 and 70 kilometers per second, how the universe is expand. And this is by measuring how the galaxy is getting far away from each other. We are doing other measurements for especially looking at far away in the universe, and especially at what we call the CMB, the cosmic microwave background. This one that you see here when the universe was a baby, was a 300,000 years old. And this is what exactly we have seen with this mass experiment, especially with Planck, which is a European project that was driven by the European Space Agency. And this is the picture that we see here. What you are looking at now is the fluctuation of the temperature when the universe was 380,000 years old. The red spots are hot, the blue spots are cold. And this is what we are trying to understand. So this is, we accidentally was founded by two scientists who they are trying to calibrate some satellites. And this is what actually you see in your TV before calibrating your problem. So you see some noise coming, and this noise actually is the cosmic microwave background that we can today measure with efficiently and precisely the fluctuation of the temperature of the universe when it was a plasma and happen and give us this what we see. So from this cosmic microwave background, we can drive a lot of parameters, and this is why we have this what we call lambda CDM model. It's a model like the standard model you described in the particle physics. We have also a cosmological model called lambda CDM. Lambda, it stands for the expansion of the universe, the acceleration of the expansion of the universe, which is lambda constant that Einstein brought to his equations to describe the universe. And then we got the CDM, it's the cold dark matter, which most of the universe is made of. So we are trying to do that. So if we back to our galaxy, so we will not, this course will not be about the cosmology, but it's basically about our galaxy. This is a picture of the arm of our galaxy taken from Paraná, from Chile, and you see that it's a full of each dot you see here in the sky, and you might see that when you go far away from the city. So you see the dot points. The dot points are the stars. Today, you should think and you should believe that each dot star you see there, it's a star, and the star, it at least has one planet surrounding it, is not many. And this is what we call the exoplanets. And imagine how many stars that we have in our galaxy and how many stars we have in the universe so far. So let's think back, let's go to the small scale. Let's go back to our solar system. You know that on our solar system, we have the sun, and we have what we call the terrestrial planets, Mercury, Venus, Earth, and Mars. And then we have the asteroid belts, when we have the asteroid objects. And then we have the gas giant planet. We're talking about Jupiter and Saturn. And then we have the ice planet. We have Uranus and Neptune. And then we have the Kuiper belt object, where we have the comets basically are coming from. This is not to scale. The distance is not respected, but this is to highlight and show the composition of our solar system. The same thing going to be on other planets and other stars. So they should have also planets, and they have debris disk. And we trying to understand from our solar system to explain the formation of the source of the solar system around. So I will not be focusing or discussing one by one here, but just what we're highlighting, showing this is just to show the composition of our star. And the same thing it should be happening on other stars billions of stars that we have on our universe. Talking about the question, are we alone in the universe? So we should, if we are asking about the existence of other life around other planets, we should be consider or understanding what is a life actually on our Earth and how it works and what we need to understand for life. And just to mention, I mean by life is not humans like us. Life, anything can grow. So I mean plants, it can be animals, could be anything. That's life. Even the presence of the liquid water as a liquid form or the organics, that should be indication of different meaning of life. And there's it be another life that we did not even understand or we don't know. We know just life that we know on our planet. But there are some criteria that we should define if we want to look for this kind of life that we have in here on Earth. So we should have a right chemical element. We should first, to make the atmosphere, to make everything works, we should need carbon, oxygen, hydrogen, silicon, and all calcium and iron, and all of the things that we need today in our life. We need to have a liquid water, not the frozen water, not ice. In the case of the South Pole and the North Pole, there is no life there because the temperature is cold, and then this water became ice, and you cannot grow up things there. So you need a really liquid water when you can have sustainable life. And also you need to have to the right temperature range, which is not cold, it's not hot, which is between 0 and 100 degrees Celsius. For example, if you go some very extreme hot places like in other planets like Mercury or Venus, you cannot sustain a life because it's very hot and you can have nothing going up within this high temperature. So, or you go to very cold place, for example, Uranus or Neptune, they are very icy objects and you should not have also life there because there's no medium temperature. So we should take into account that's one. We also need an atmosphere, especially the magnetic field, which is protecting us from the energetic particle that's coming from the sun or coming from the universe. And also we should have a very enough gravity. So we should have the object is big to maintain things, to hold things. For example, if you go to the moon or to a smaller object, so you cannot just stay on the ground, you will be just ejected in the space because there is no enough gravity taking you to the center like what's happening on to the Earth to help us to build the buildings and to have everything installed on the ground of the. If we have all this criteria, so we can consider ourselves, we are in what we call the habitable zone. And this is a new definition, a very simple definition of the habitable zone around other stars. So now it means that if we're looking for life on other planets, this should be fitting this criteria or exist in the habitable zone. Let's explore some habitable worlds in our solar system first. We will talk about Mars because it's our neighbor and it also exists in the habitable zone. We have Europa and we have Enceladus, one of the moons of the planets, and also we have our planet of Earth. So let's Mars is closest to us and it's supposed to have also life on it a few billion years ago. And something that's happened to Mars is that it might lose its atmosphere. It's somehow, and then it lost when you lost atmosphere. So you will lose what it protects you from this from the solar radiation, and the atmosphere. When the Mars lost its atmosphere, then it lost all the water on it. So, and we believe that there is traces of atmosphere of this traces of life on Mars. So, and then we'll talk about Europa and Enceladus. So, and also Titan, one of the moons of the Saturn. So Titan is the only moon that it has an atmosphere in our planet. And this is the left picture you see here is the picture taken from the ground by a spacecraft that was sent to the ground of Titan. We have also the atmosphere. We have the atmosphere of the moon, of the Titan, and Titan actually it's an object which is made of oceans or lakes, but not of the water, but of the metals, and we can see them here. That's a real picture. And why the atmosphere is very important because it's maintained this equilibrium of the temperature, like for example that we have on our Earth. Without atmosphere, you cannot maintain that equilibrium temperature that we have in our planets. So the atmosphere is a very strong condition to have for example, a sustainable life or sustainable equilibrium in this planet to talk about life. Then we have Enceladus. Enceladus, it's a very icy object, but yet we have observed if there is this plumes coming in from it. And these plumes are like jets of what we call the organic matter on it. So this organic matter is basically coming from an ocean, which is, we believe that it's under the crust of this Enceladus. And where this coming from, this plumes, we believe that's coming from what we call the hydrothermal vents. And this hydrothermal vent are small volcanoes happening on the bottom of the ocean we have them also on Earth, something like that. So, and this is what the hydrothermal events, they are produced by small volcanoes under the bottom of the oceans, and they are producing this organic matter that escape the crust of this Enceladus and then escaping, and we can observe them. So I'm bringing this example because under the ocean we have example of this. We have some animals living in this extremely events under the ocean, like bacteria, and we have some many other animals living under this bottom of the ocean. So the question is why this should not be also an Enceladus. So that means also that we probably having some kind of life under the bottom of Enceladus so far. So this is two examples that I would like to highlight. So for example, for Enceladus and Titan and Mars, this is the most or the potential object that might have the life on beyond in our solar system. But there is not only planet in our solar system. There's also other planets around other stars. So if we raise the questions, how many stars that we have in our Milky Way, the numbers it's go to 100, from 100 to 400 billions of the stars. So, and today we believe that there is around each star, there is at least one planet. And the first exoplanet was discovered. It was discovered by Michel Mayor and Didier Queloz, and this was 51 Pegasi b. And this is the first time, was in 95, that we know that there is exoplanet around other stars. And for that, they got the Nobel Prize back in 2019 for discovering the first exoplanet around other stars. So today we have more than 5,800 exoplanets discovered so far, and discovered by different methods. So, and you see here the method that we discovered. They have transit method, the radial velocity, macro-lensing imaging, and the principle it's basic. So it's we look at the star, the brightness of the star. When we got a diminution of the brightness of the star, means that there is something passed between us and this exoplanet. And by the way, this is the statistic of the discovery of the star, of the exoplanets with the method we discovered. We have many other methods, so I highlight some of them, especially the transit method. The transit method is simple. So when you have a planet coming between you and the star, so you have diminution of the light. If the planet is big, you have the diminution, it's much deeper. That means you have a very large planet. And this is the way we discovered this exoplanet. We called it transit method. There is also the imaging, direct imaging. We look at the star, we block it, what we call coronagraphy, and then we look at the stars behind it. And this is very rare method to do. And also you need a very large telescope to do. You cannot do with the small telescopes. For example, in likely to the transit, you can find it with small telescopes. For that, we need large telescopes, like the extremely large telescopes. This is the European telescope being constructed in Chile. It's have a diameter of 39 kilometers in its size of the mirror. So it's allow us to find this objects that they are far away. So for now, we targeting this, what we call the habitable exoplanets. So we found many of them. So but not all of them, but 4% of them are terrestrial planets. So just to know, this is the planet, the closest planet to us. It's about 4.2 light years away from us. You know how much that's far away. Light years is the distance that light travel in a year, and the distance in the light travel in 300,000 kilometers per second. So this means if you wanted to go to the closest planet, it will take you 4 years if you are going with the speed of the light, and speed of the light is 300,000 kilometers per second. For example, the light we see now in the day, it's coming from the sun. It took at least 8 minutes because the sun is 150 million kilometers away from us. So that means even we discover the life somewhere, even in our closest planet, we will be never going there because we don't have that technology to go there. So mean that there is no plan B for our planet and we cannot go somewhere else. We're just discovering and trying to understand if there's other potential lives on other planets. From the system or from this sample of planet that we have found so far, so I will talk about the TRAPPIST one. TRAPPIST, because we have contributed to discovery of this exoplanet system, is this first time that we are finding a solar system with 7 planets, not 1, not 2, 7 planets. So this is, we call them TRAPPIST, and TRAPPIST is a twin of the telescopes. One is located in Chile and one in Morocco. So we're finding this, what we call the exoplanet. So, but it's the most important thing in the 7 planets is that 3 of them, exist on what we call the habitable zone. D, E, and F are existing on what we call the habitable zone, which is not far away from the sun, from its stars, and is not close to its stars. So the way that we discover them is using the transits method. So we see these gaps here, and these gaps indicating that there exist of many other planets around the stars. And the stars actually, it's almost like 40 light years away from us. If this system, if you take it, all of its TRAPPIST-1 system with 7 planets, it will fit under the Mercury orbit. That means the stars that orbiting around this planet is small compared to our star. We call them M dwarf stars, which is much smaller than our planet. And they would like to see that the green and the area is the habitable zone, which is when you have the water on a liquid form. So if you are getting closer, you will have hot temperature. It's not a habitable zone. For example, the case for Mercury. So the temperature, it goes up to 600 degrees Celsius. In Venus, it's 800 degrees Celsius because it has an atmosphere. Or you go far away from your planets, you have a very cold temperature. Simply, the habitable zone is when you are not far away or closest to your star. And that's just the right space when you can form any kind of life that, as we know. If we wanted a projection of this planets, for example, in our solar system and in other systems around the stars, we see something like that. Habitable zone is changing with the change of the type of star. Star, if it's big, it's going to be hot. If it's small, it's going to be less hot, but does not mean it's hot. For example, the temperature of our star is around 5,000 degrees Celsius on the surface, of course. In the core, it's much higher. For example, what we call the M dwarf stars, they have less temperature, but still thousands of degrees Celsius, does not mean that it's cold, it's cold. This is why we call them M dwarf stars. So this habitable zone is changing with the change of the brightness or the temperature of the star. For example, you see that in our solar system, we have the Earth and Mars as one that exists on the habitable zone, while the rest of the planet, they are not exist on the habitable zone, either Venus or Mercury or Jupiter, Saturn, or other planets. This is other example of other planets surrounding other stars that exist also in the habitable zone, including the TRAPPIST-1 that exists there. So what about life on this exoplanet? So how we can find an exoplanet does not mean that there is life there. So we should fit this criteria that we were talking about. We should find it if they have atmosphere, and this is the most important thing. So how we can find this atmosphere, even we are not looking directly to this exoplanet, we are just finding them indirect way, just by looking at the diminution of the light and of the stars, and we don't see them directly because they are far away. So there is, as scientists, they are developing ways how we can study the atmosphere and everything through the light that's coming from the star. When the light came through from the star, came through the atmosphere of the exoplanet, they will excite or absorb. The molecules in this atmosphere will be excited or absorbed by the light, and then we can give us emission or absorption of these molecules that we can see which type of molecules exist on this exoplanet with this, what we call the transmission spectroscopy. And to do that, we need also very large telescopes, like James Webb telescope that we have launched recently, or we use the ELT, the extremely large telescope, which is going to be ready this year to collect the data so far. This is our very expensive telescopes. For example, James Webb telescope is costing almost $10 billion or 10 billion euros, which is a very expensive project. And also the extremely large telescope was built by the European Observatory, which cost almost 2 billion euros. This is a very expensive project to look for this interesting topics like the existence of the atmosphere of this exoplanet and so far. The Chinese also, they are building one of the largest telescope in the world, which is like 500 meters in diameter, which is between mountains. And this is when we'll be looking for the atmosphere of this exoplanet and also looking for the signals that might be coming from outside, from some civilization, other civilization. So the way how we study this atmosphere is very simple. So we look at this atmosphere of this exoplanet when they're transiting. And this is what we call the transmission spectroscopy at different wavelengths. And that can give us an idea about the composition of the atmosphere. And from the composition of the atmosphere, we can know if there is some biosignature or some effect that producing this atmosphere. So for example, if you look at our planets, you find oxygen, you find nitrogen, and this can give you an idea which kind of life that could be on this exoplanet. Even we will never be able to look at the salt or the ground of this exoplanet so far. So from the atmosphere, we can tell if they have liquid water. For sure, we should have detecting, for example, the water as a vapor on their atmosphere and so on. We have done that so far with small telescopes and large telescopes, especially Hubble and James Webb, and we have found some molecules so far, like the methane and like HCN and other molecules so far. And this was found on WASP 19b, one of the famous exoplanet that it's a terrestrial exoplanet so far. And this is their spectrum. As you can see, we have different molecules found on their atmosphere. And this was taken also with James Webb. You see the water vapor and this, for example, WASP 39b. So when you see B, this is the first planet that we found around its star. C means the next second planet, D, it's making the third planet, and so on. So you see that we have found the water, CO, and also many other molecules like sulfur dioxide or like or carbon monoxide, and all of this give us an idea about the sodium, and thus this planet they might host a different form of life that we can have so far. So I'm bringing these slides to show that we have found phosphorus, for example, on the star formation region on other stars and on other planets. And this phosphorus is actually, it's one of the building block of our DNA. So that's mean, and we have also found it on comets. And comets, they believe that they are icy objects, they are leftover of the solar system formation, and they might bring the life to the Earth. This is a very an outstanding question that we still did not understand yet. For example, the comets are made of ice, which is water, frozen water, and we believe that we still not explain how we got water on our planet. How could water survive 4.6 billion years in our planet? But we believe that the comet, they might play a very role in bringing the life from to the Earth, because this comet is also full of organics. So we have many organics that we have that build in life on Earth. And the same thing that it's may playing a role in delivering life to the other exoplanets. For example, the cases that we have here. So this is why this is actually was the topic of my PhD. So as Abdullah mentioned, so I was working on studying the chemical composition of comets and trying to understand how comets, because they are frozen objects and they left over from the formation of the solar system, how they might contribute to the life that we have on Earth, bringing water and also bringing organic, because most of the organics that we have in our planet exist also on this object. And why I'm saying that, because our planet, it runs through many dramatic, catastrophic also events, seismic and tectonic, and all of these things happen to them. It will not make them sustainable if the life exists in the first place. So there's maybe external factor, which is a comet demise when the planet established in its term of activity. So it's the comet that gets an impact. And this, we can't find the evidence of this impact craters that we have in a planet. Like, for example, if you go to Arizona or you go to some place in Africa, you find these very craters that we might be the impact of this object very early time. And also, you might heard about that this object, there might be a problem in our trait or our life on planet, and this is also especially asteroids, because asteroids, they are different from comets and they are made of rocks, and we believe that also we have behind of extinction of dinosaurs at some point 60 million years ago, because that's the way how the geologists cannot explain how we get out of dinosaurs in our planet, and could be of this object, and they still present a danger on our planet today. Recently, a few days ago, we have a really closest asteroid coming closest to us, but it's already passed away and we are safe. In April 2029, we have also another object coming closer to us with low probability of impacting with the Earth, and still we have many other objects that, because this in space, there is no peace. So there's a lot of things happening. There's a lot of asteroid and object moving around and so on. So recently, back in 2017, this object we're talking about now is that we are object within our solar system. In 2017, 2019, this is the first time we find that objects coming from outside of the solar system. We call them interstellar objects coming from the outside. In 2017, we found asteroid, and it's called Oumuamua, and that's mean a new visitor in the Hawaiian language. This is called Oumuamua. And then we have Borisov, it's a comet. So that's was found in 2019, and actually it was found by this Ukrainian amateur astronomer. It's called Borisov, and that's two objects. They change our way how we think the life that might exist on our planet. That means that if maybe the life is not even originated from our solar system, but probably it's coming from this other object, from other solar system. So this is maybe, and who brings that life to our solar system is maybe through this object, what we call the interstellar object. And there is a long debate now, it's going on. If this are natural object, are asteroid and comet, as we understand, or there are some, for example, there should be some extraterrestrial aliens that come and visiting us, because these two objects, they were accelerating. Borisov, it's 100%, it's a natural object because it's sublimating like a comet, like as we have also solar system comet. Oumuamua is not sure because it's not an active object, and also this is not an illustration, it's not a real shape, but from its rotation, we understand that it has a circular forma. So there is a book by one of the famous authors, it's called Avilov, who wrote a book about this, arguing that Oumuamua is aliens, not a natural object, and that's complicate the question about the origin of life in our planet, and because everything is moving and we're trying to understand that. So I will not be taking much time from your sources. We kept it short, so they will stop here and take any, if you have any questions related to all these topics. Thank you very much. So Abdullah, I'm not hearing you. So if you have any questions, I would be happy to answer.
Thanks you for reminding me. Actually, I was talking, but so thank you very much for this delightful conference and talk. I actually, and also wonderful slides. I actually learned a lot of things. So before I start with my question, I think I will give the chance to the online audience if they have any questions. Est-ce que vous avez des questions, les personnes qui sont en ligne? Questions, remarques ou observations? Donc,
yeah, I know this might be not common topic for all of you, but if you just have any wonderful questions, I will be happy to chat about. So either about the evolution of the universe or the question of searching for life beyond Earth, or any kind of this question that you might have answers, so you might have questions about. But just to let you know that we don't have answers of all of the questions. So we still have many questions remain open. So like, are we alone? All those questions that I raised at the beginning, they're still like open questions. So we still did not understand. Like we still did not understand many other things in how science works. So we still just building new observatories, improving our technology to address these challenges, this question, to understand it. And I think this is a nature in humans. So, you know, we are trying always to wander around ourselves. So you might ask this question. So what we can even find the life? What we're gonna do? So we have nothing to do, but just we are improving our understanding where we are from. This is like kind of a mix of science and also of philosophical questions that we still have not understand yet.
Yeah. So if, so if there is no question, so I will
Yeah.
give. So here, vous avez des questions? Sinon, moi je prends le temps, comme ça vous aurez le temps de réfléchir. Alors, so something in English, so maybe I will also give the question in English. So I think most of you doesn't know, but there is something in the planet that calls also Youssef Moulane. So can you just tell us about this planet has your name? Or
Yeah,
I
thank
don't
you
know if
very
it's a
much.
planet or exoplanet. Maybe I know there is something in the space that has your name in it.
Yeah, thank you very much for this. Actually, this is an asteroid. So, and I did not talk about much about asteroid, the small ball, the object or rocks that we were talking about now, that we might be create of our life on the planet. I have one, yes, under my name. Its number is 33903. So if you type that, you will find it, Youssef Moulane. So this is was like an honor from the International Astronomical Union. So like honoring people who working on the field of the planetary science, like working, describing or characterizing comets on asteroids, trying to understand all this question. So they disturbed these names, giving names to the asteroid behind, after names of some scientists, and there was one of them. In Morocco, actually, we have 7 scientists who have their names, and also we have a lot of French people, and we have Mari, everybody working the fields, making some difference in the having an honor to have the names on their asteroid, name of asteroid after their names. So if you type mine, so you'll find it. It's a very large object, which is like 18 kilometers on its diameter. So, and I hope that asteroid will not hit the Earth at some point. Otherwise, all the shame will be on me. Even
Yeah,
I
so
have nothing to do with this one.
I hope not. So I have also another question, which is so I think next week we will have also a talk on the new planet that is being discovered, will be given by another scientist. Can you, before this conference comes, can you just give us your thought about this discovery?
Which one? Which one?
I think there is a new planet which is called Pluto. No, it's in the which is in our solar system. I think I forget its
Yeah,
name.
because there's many discoveries going on. So in this
Yeah,
field, there's like, for example, for exoplanets, every time we now increasing the
I
number.
think
The first exoplanet was discovered in 95. Now we are finding almost 6,000 exoplanets so far. So there's always things going on.
uh, so or maybe alors est-ce que vous pouvez me dire le nom de la prochaine conférence, pardon? Euh, la planète, comment? Neptune. Oh, voilà. Donc, alors, voilà, je vous.
What is that? I could not hear that. Well,
Neptune, qui est la planète trouvée au bout de la plume.
can you repeat again?
Neptune.
Oh, Neptune, yeah. So Neptune is one of the Neptune one of the ice planets. So and yeah, so maybe I did not have time because to go through all of that, I will just give you like shots from everything. So because, for example, each planet, if we want to describe it, will take more time. So in this next conference, you might have like more details about, and also we can that have also later. So you can have details about each planet. So what is they are made of, and what is their composition, and how it works, and what is their characteristic, and so on. For me, I just give you like a shot of everything. This is why I called my talk the brief journey through the cosmos. So you will give you a little bit from everything. But of course, if we need to go in details for each one, so we need more. We need a series of conferences because, you know, in space, there's a lot of things going on. So even the stars, we have many different stars. In the galaxy, we have different kind of galaxies. In the planets, we have different kind of planets. Everything is like a variety, and we still did not know all of them. This is like, on all of this, what we were talking about, is represent only 5% from the known universe. We still don't know 95% of it.
Yeah. Yeah, actually, the universe is very big. Even I don't actually know all of them. Still, I actually try to understand each time to learn something new every day. There's also something that is actually very recent, which is the discovery of this hard particle. Since I have a background in particle physics, s- do you aware of it? And you know this is called uh, the ultra high energy neutrino.
Yeah.
Uh, so the discovery of this new particle, high ultra energy neutrino, what can it give us a plus in our understanding of the universe, in your point of view?
Yeah, this is the neutrinos. Actually, this is the kind of particle that they are very energetic, and also they don't interact with matter. So this is why we can't see them. So, and there was a big discovery last few weeks about this. This is the first neutrino ever detected with this high energy. So like 200 PeV, and was just discovered by this experiment called Chem3net. This is one of the telescopes under the ground, under the water, and they dedicated to observe this kind of particles like neutrinos. So these neutrinos, they have in their press conference, they mentioned that these neutrinos might come be from different space region. It could be from an explosion of a star, or for example, like what they explained is that it's just like interaction between two stars and they explode. And this neutrinos was interaction with the CMB with photons and giving this high energetic neutrinos that we have so far. So neutrinos are very hard things to deal with because don't interact with matter. For example, the light interacts, everything, all the muscle particles, but this one, the neutrinos, they don't interact. So this is why we need to build this experiment underground to win this object, because every time for now there's many neutrinos passing through us, so they don't interact. So you have to really have a sophisticated experiment to find this object, but also they can give us insights because they produce it in the high energy collisions in space. So, and we can use them to try to locate the nature of these explosions and how we can get them from, and so on. So this is another domain of which can bridge the high energy physics and also the cosmology, because you know that after the Big Bang, so we formed the first particle, the first the bosons and the fermions, and then we formed the nucleus, and then we form other matter that we see today. So in cosmology, we are very interested also to knowing, because we still did not know, for example, this dark energy, it might be another form of particle that we cannot find it, for example, or dark matter. It can be something that we did not find a way how we can find them, but there should be also some particle physics maybe existed after the Big Bang.
Yeah, thanks you very much. So it was very clear. Can you just give the student in a very demystified manner and simplify manner the recent research that you are conducting and that are the research area in the astrophysics today?
Yeah, so I'm working on two projects for now. So the first one is the comets that I told you about, and the planetary science and the exoplanet. That's what we have talking about. That's my expertise in. We call it the planetary science. We're also interested in developing the planetary defense, trying to find a way how we can defend ourselves from this asteroid and comet that they might come to the Earth. So there is like we don't have time to talk about them, but there is like some developing some solutions and to how we deviate this object from their orbits, and also I'm understanding the comets and how they contribute to the life, for example, on our planet. This is the first research topic which is covered the planetary science. And then now, as I came to the UM6P here at Morocco, so we're developing another research project about the CMB, the cosmic microwave background. The first picture that I showed to you, we still did not understand a lot of things about the CMB. And this is the CMB is the finger print of, or the print fingers of the Big Bang. So when the Big Bang gets happened, we're looking at the temperature when the universe was all very baby. So we're trying to understand a lot of things and we are developing a project on that here in Morocco. So, and with some colleagues also from the University of Paris City. So to understand, for example, find the gravitational waves that caused by that Big Bang. So you know the gravitational waves are the waves that produce it when you merge two very large big things, and they produce waves in space. And we have detected that, for example, between black holes and between neutron stars. We also believe that when the Big Bangs happen, and if it's happened, it should produce also this waves. And this wave, we should find the pattern on the CMB. And this is what we're trying today to improve the instrumentation and to improve the technology to find this gravitational waves on the CMB. And this is going to be a very strong evidence about the existence of the Big Bang so far.
Thank you very much. So, est-ce que vous avez d'autres questions? Et en ligne, est-ce que vous avez des questions ou commentaires?
Vous pouvez les poser en français, donc je n'ai pas de problème de répondre en français, mais juste pour la conférence, j'ai l'habitude de le faire en anglais, c'est pour ça. Et vous pouvez aussi raise your hand, you can lever la main si vous avez une question online. C'est comme ça que je peux voir aussi.
Apparemment, il n'y a pas de questions. Alors, est-ce que vous pouvez me donner un petit résumé de la conférence en français ou en anglais, comme vous voulez?
Oui, donc encore une fois, je vous remercie pour m'accueillir pour cette conférence-là que vous avez organisée pour les étudiants, et je pense que ça ouvre aussi l'esprit des étudiants d'avoir plus d'informations sur notre cosmos et voir si ce qu'on fait comme des chercheurs astrophysiciens, on fait beaucoup de choses. Donc, dans cette conférence, j'ai parlé un peu sur l'exploration, ou bien une petite journée dans notre cosmos. J'ai parlé un peu dans le Big Bang et aussi la création, ou bien de l'origine ou l'évolution de notre univers, c'est ce qu'on appelle la cosmologie. Et j'ai parlé un peu sur aussi la recherche de la vie d'ailleurs, et ça, c'est la recherche de la vie sur d'autres planètes, ce qu'on appelle les exoplanètes, c'est des planètes qui sont autour d'autres étoiles. Et aussi, on a parlé un peu sur la vie, l'origine de la vie sur Terre, et pour comprendre, pour trouver la vie ailleurs, il faut qu'on cherche d'abord comprendre l'origine de la vie sur Terre, et surtout à travers les petits objets qu'on appelle les comètes, qui peut-être qu'ils ont contribué d'avoir la vie sur Terre. Donc, ça, c'était brièvement les points qu'on a abordés aujourd'hui dans cette conférence. Malheureusement, on n'a pas beaucoup de temps pour parler en détail sur d'autres choses, mais ça, je pense que vous avez d'autres séries de conférences. Là, vous avez accueilli d'autres gens pour parler plus en détail sur ce genre des questions qu'on n'a pas encore répondues. Et je veux juste souligner qu'il y a beaucoup de choses à faire dans ce domaine d'astrophysique. Si vous êtes intéressé pour faire une carrière en astrophysique ou en astronomie, on a pas mal de questions à répondre. On a aussi des expériences, aussi des télescopes qu'on est en train de bâtir pour répondre et pour répondre à ce genre des questions qu'on n'a pas encore une réponse.
Super. Il faut aussi noter qu'en France, il y a pas mal de laboratoires et de recherches dont les ingénieurs sont aussi fortement appliqués.
Oui,
ouais.
ça c'est important de souligner, parce que dans l'astronomie, tu as toutes les métiers en fait. Tu as des ingénieurs, tu as des gens qui font la science, des ingénieurs qui fabriquent ou qui designent, par exemple, les satellites, ou bien les space télescopes, les télescopes spatials, ou bien les télescopes dans le ground, ou bien des mechanical engineering, electrical engineering, tous les types d'ingénierie qu'on a besoin pour faire les expériences aussi, soit du CMB ou d'autres expériences. Et aussi, on a besoin des chimistes. Il y a des gens qui font de la chimie, comme moi, j'ai fait de la chimie en astrophysique. C'est pour ça qu'on appelle l'astrophysique ou l'astronomie une science globale. Donc, tu as des gens qui font biologie, ils peuvent faire astrobiologie pour chercher la vie d'ailleurs. C'est biologique, on parle de la biologie, la chimie, donc chimie, la chimie, physique, mathématiques, bien sûr, pour le mouvement des planètes, et aussi l'informatique. Aujourd'hui, on fait l'IA, l'intelligence artificielle, pour, par exemple, classifier les exoplanètes et les étoiles. Il en a besoin de tous les domaines. C'est ce qui est bon dans l'astronomie. Tu vas trouver toi-même. Et aussi, si tu fais high energy physics dans à un certain moment, tu trouves aussi de parler sur le Big Bang, de cosmologie et ainsi de suite. Donc, c'est pour ça l'astronomie ou l'astrophysique, c'est un champ qui est global, qui contient toutes les disciplines de la science en général. C'est pour ça, dans l'ancienneté, tu trouves des philosophes ou bien des scientists qui sont experts en chimie, en physique et en mathématiciens, et ils sont des astronomes aussi, parce qu'ils comprennent tout.
Oui, oui, c'est ça, c'est un domaine qui est assez large, en effet. Ok, donc je pense on est à l'heure et je vous remercie fortement pour votre présence et votre engagement. Et
Merci.
voilà, donc si vous n'avez pas d'autres questions, commentaires, donc je
Et,
veux dire au revoir. Oui, oui, oui,
et
oui,
merci Abdoulaye. Si vous avez d'autres questions après, donc vous avez mon email, donc c'est
oui.
moulaneyoussef@gmail.com ou bien youssef.moulane@qm6p.ma. Donc vous pouvez m'écrire par email ou bien si vous me suivez sur LinkedIn, donc je peux répondre à vos questions après, si vous avez d'autres questions après.
Voilà. Donc, en effet, dans les mails que j'ai envoyés, il y a la page de Google Chrome, Google Scholar qui contient toutes les informations sur l'astrophysicien Youssef Moulane. Vous pouvez le contacter soit sur son compte LinkedIn ou soit sur un email comme il l'a indiqué. Merci et je vous remercie deuxième fois et voilà, je vous dis au revoir et merci. Bonne journée.
Merci à vous. Au revoir. Bonne journée. Merci.
Au revoir, merci beaucoup.
Merci.